Hi, I'm Bill Magro. Thanks so much for the invitation. And I'm actually thank you to all the people who actually stayed to the end. It's not always best to be last. My updated title, I'm not sure if it made it onto the webpage, is AI and cloud, HPC's friend or foe. Because there's a lot going on in this industry right now, and it's not always clear what's helping, what's not, and where things are going to end up. There are a lot of interesting and maybe unexpected things that happened over the last decade that put us where we are. So what I want to talk about is kind of how we got here. And there's a lot of people in the room who experience this and live this, so it won't be new to you. For some other folks who may learn something or experiencing something new. But then we're going to spend the second half really talking about, what does it mean? Where's cloud helping? Where's cloud potentially causing a risk to the trajectory of HPC, either to the industry or individually for the things we do? And similarly, AI, where's it helping and where is it maybe causing some challenges? So a little bit about me, since you were asked, I didn't attempt to follow the formula, but an interesting thing most people don't know about me is that I've had like 6 brushes with death. And so here's a few examples. This is a beach in Bali where I got swept out to the ocean and I had to swim for my life so I didn't get crashed onto those volcanic rocks at the end. In Hawaii, I got picked up by one of these very dangerous things and literally dropped on my head halfway up the beach. And I noticed the sign warning me as I was leaving. In Japan, I was struck by a pit viper, which is a close relative of a rattlesnake. And as I climbed out of the mountain, I found this nice poster warning me, poisonous snakes, pit vipers. And of course, I was traveling with my son who had planned the trip, so we did not have a first aid kit. And we were 2 miles away. And then another time with my son in Japan, he was telling me about bamboo shoots. So this, I was like they have in Chinese food? He goes, yeah. And I stepped on one of these and I ate it. What I didn't know is they're full of cyanide. So I got cyanide poisoning. So that was an interesting evening, but eventually it wore off. And then, no, I wasn't almost killed in my Zed. One of my hobbies is woodworking, so that's some furniture I built. How to cherry. So, okay, well, I'll take that. I don't know what they're plotting. So this is something everyone should be pretty familiar with, but this is that right-hand turn, as Intel called it. In 2002, we were on this trajectory of up and to the right with frequency. Ron just talked about it, and abruptly surprised the world and said, we can't do this anymore. The frequencies are too high. The power density is approaching the surface of the sun. We have to make this right-hand turn. And this is, the other day on a panel, I talked about the fact that the only way we could convince developers to embrace parallelism was to say, everyone else is going to be on this curve, and you're going to be on this curve, and your pain is going to grow over time if you don't embrace parallelism. And it took over a decade, and many people didn't adopt it, and other things came in and replaced their software. So this is the same chart Bob showed the other day, illustrating the 1000x growth per decade that HPC systems were experiencing. But what I've done is I've actually overlaid some of my own lines and trying to illustrate where that tailing off occurred and became really noticeable to the HPC community. I would argue sometime around 2006 is when it first became visible and people started noticing. So that set us off on this, oh my gosh, we have to figure out how to get to an exascale because the next 1000x is not going to be free. And it became an international race, of course, because of the national security, prosperity, competitiveness aspects of high-performance computing. So these are, I think, up to date. I updated Lumi based on the November results. But we have exascale machines now. But the path there was not super straightforward. One of the key points, I think, was the moment when people started to really embrace parallelism. It was already signaled with multi-core, but we saw like the Roadrunner system, right, with the cell processors. We saw this study, the Keeneland study that Jeff Fetter, I think, chaired, coming out of Oak Ridge and Georgia Tech, where they really started to think these GPUs could actually be useful for HPC if only they had a few things, right, like reliability. We're still working on that. Double precision, ECC protected paths, and they worked with some early GPUs. And that's where I think really the first time I heard that somebody said this could be a viable path forward. So this set us on this path to exascale, and I had a lot of fun building this timeline a couple of years ago. But the key things, and kind of highlighted in color, are, parallelism really starting to come in a strong way. The Exascale initiative, the Exascale report, some extreme machines like the Tianhe in China with 3 million cores, realizing the memory had to keep up. So first MCD RAM and then later HBM. Then the programming model saying, we have to make this simpler. We can't just have CUDA. And so AMD came out with ROCm, Intel came out with one API, and then ultimately new architectures, NVLink to try and get around some of the bottlenecks, and then ultimately tightly coupled CPU, GPU, things like Grace and Intel's Falcon Shores to deal with the programmability issue and the heterogeneity and Amdahl's law. So it's been a long path, but this year, right here, 2012, was kind of an interesting one. We'll come back to that in a moment. So meanwhile, the folks off in cloud were doing their own thing, right? They were happy as pigs in mud because they were building these 30 megawatt data centers. You put 60,000 servers in them, 120,000 disks. The number of cores were going up and up and up. You don't need to do type coupling. And so you're getting this 1000x and enjoying it for 20 years themselves. And that was all great until basically the improvements in for core performance, the memory, cost per bit, everything just went flatline recently, right? We're not getting the gains anymore. But the other thing that happened in cloud that was interesting and I think relevant to the high-performance computing community is that because the traffic was unpredictable, because it was no longer just up, there was lots of east-west traffic coming from all kinds of different workloads. The major cloud providers, this is from Google, but Facebook did the same thing, started building fat trees at every level through their network. So in this case, these are racks with top-of-rack switches. These are multi-level fat trees in here, and then those go into multi-level fat trees, which in turn keep going up and up and up. And so we were starting to get HPC, I would say, inspired networks showing up in the clouds, even though HPC workloads weren't running there. So in 2012, something interesting happened, and that's when the ImageNet was won, right, by people who rediscovered and applied and implemented the convolutional neural networks, and were able to get a kind of a step function in accuracy in ImageNet, doing the image recognition. The classic is this a cat or a dog. And the reason that was able to happen, of course, is because these GPUs had become much more powerful because HPC had invested in them. Because Department of Energy and other labs around the world were buying these for HPC, they became plentiful, they became more capable. So in many ways, HPC triggered the launch of the latest AI revolution. So we've been on this path of 1000x every decade. What happened next? The AI community just took off. And instead, it went 300,000x in terms of the demands to train these models in just 6 years. That's a big number. That's really fast ramp. So as you can imagine, that got the attention of the vendors, that got the attention of the cloud providers, got the attention of the world. And then in 2017, as we discussed the other day, that's when this really key paper called the Transformer paper came out. Attention is all you need. And I think Doug was mentioning it the other day, saying just trial and error. Well, I think there's more to it than just trial and error. There was an insight there, and it seemed to work, which is the idea that if you think about how humans learn when they're very young, all they're exposed to is just a stream of information. And think about how we all behave. We try to guess the next thing we're going to hear. And when someone says something unexpected, we experience surprise, and a different part of our brain lights up, and we learn. Sometimes it's funny. Sometimes it's something that triggers an insight. And so they decided to try this. Just your only way you get rewarded is predict the next token. And it turned out something magical happened. The other thing they did is they figured out how to move from what's called dense activation to sparse activation. So traditionally in a dense or in a deep neural network, the CNN, you have to activate the whole network to do the inference. And they found this way to weave their way through and only touch the relevant parts. And that was called the pathways paper. And then the last thing was, rather than training on a specific data set, just feed it as much information as you can and try and create something general. And that's this notion of foundational models. And so those were the innovations in 2007. And that triggered, of course, what we saw with GPT-3 and a bunch of other models. As the models grew and got to bigger and bigger, in the case of Google's Palm 2, which is what I'm illustrating here, we trained it with more and more parameters. What we saw is emergent capabilities, moving from simple reasoning to being able to explain jokes, to be able to tell jokes, to doing arithmetic, having multi-turn conversation and code completion, just all these things that we're all so excited about that we see through these chatbots. These just emerged, and I don't have time today, but there's places for each of these, I'll call them not modalities, but these types of tasks and interactions where you see step function increase in performance of the model as you reach a certain threshold in parameters, and they're not all the same. So this one, it was truly an exascale problem to solve. Google shared that it was 2.56 yottaflops that it took to train this model, 540 billion parameters, and this was run on our TPUs, but roughly it was the equivalent of keeping an exascale machine busy for a little over a month. So that's similar to some of the other numbers we've heard quoted this week. So now we've just experienced a 300,000 increase in 6 years. Well, for the next 5 years, we saw 5 more order of magnitude increase, and this is in the parameter count. That doesn't mean that it's the computational amount because, depending on the model and how much you're feeding it, it's not a one-to-one. But the point is that we're still seeing this 10x per year trajectory in terms of the scale of the models. And I stopped here at Palm, the 540, which was the largest model trained to date when we made this graph. But you'll see some other things here like BERT, which was one of the first ones, GPT-3, Megatron. We've heard about that this week. So in this decade, cloud was on one path, HPC was on a different path with the Exascale program. They both changed dramatically. And AI rose up in the middle of this, somewhere at the intersection of HPC and AI. So now it's a good time to kind of take stock and say, where are we and what is the state of affairs and what do we need to be thinking about? So the first thing to observe is that exascale systems, and I saw this through my participation in the Coral program and the Exascale program, the thinking of what those machines needed to be able to do actually evolved as the program evolved. A lot more AI, a lot more data analytics came into the conversation. And we see that in the architecture of all the machines. All the machines are these CPUs tied to a collection of GPUs. The GPUs are very tightly coupled. There's a lot of networking, and the network is very close to the GPUs. At the same time, because cloud systems were growing and dealing with the traffic patterns I described, and having to get HPC-like networks already, or at least topologies, dealing with problems of scale in believe it or not, a much larger scale than the exascale machines, although you can't compare them one-to-one. One is capacity, the other is capability, and beginning to support these AI workloads, whether directly through things like CPU and GPU platforms, or in the case of Google, with custom TPUs, cloud systems started to have to deal with HPC issues, tightly coupled problem issues. And so they keep inching closer and closer together, cloud and HPC. So we're not done yet. This is a nice graphic that I got from this site called lifearchitect.ai, which is a trove of information about just all kinds of stuff going on in the AI world, lists of models, their performance, even lists of jokes being explained by different chatbots if you want to read good jokes being explained. So this is GPT 3.5 Turbo. This is a smaller version, but it's what's behind ChatGPT, the original one, 20 billion. And then for comparison, this is how much larger ChatGPT 4 is. 1.76 trillion is what they report. This is the Gemini one that was just mentioned, 1.5 trillion. Ernie here is being worked on, I think, by Baidu in China. Olympus, I think, is coming out of Meta. And the real question is, what's next? How big can these get? How big do they need to get? When do we stop? Right? But for the foreseeable future, it's up and to the right in terms of the demand. And so you're going to see the cloud providers continuing to build bigger and bigger GPU and based supercomputers, and then case of like Google TPUs and other cloud providers have their custom silicon as well. So let's shift now to this whole question of, is cloud helping HPC or is it hurting? And similarly, we'll go through AI. So let's talk about some ways that cloud's helping HPC. First of all, the obvious one, elasticity. Being able to deal with urgent computing. We've talked about that like in emergency situations. I have an example I'm going to show you in a moment. Also just making everyone more productive by getting rid of queuing as much as possible. The most precious resource we have is ourselves and our time. And to sit and wait in a queue makes you less productive as a scientist or engineer. I know when I was a user of the big HPC systems that I would only submit so many jobs. And after a while, I didn't submit more jobs because I knew that by the time this job ran, I'd have these results back and I'd probably want to ask a different question. So there's a natural tapering that happens when a scientist is dealing with a queue. And if you can unblock that and just give them access to resources and quick answers, they can iterate much faster. So that's one way that cloud really helps. Another one is efficiency, which is when you purchase and this relates to choice, when you purchase an on-premise HPC system, you have the world of options. But for the most part, when you're done, you buy one thing or maybe two. And so at that moment, everybody brings their workload in and it's a blended optimization. Cloud is just the opposite. Cloud has access to the world. They down select to a large number N, might not be the one you wanted, but then your users still can find one that's the closest match. So one of the things cloud can do is actually help you augment an on-premise choice. You know, you made some compromises for some subset of users over here. When you made this, you put those users and match them to the right infrastructure and get more efficiency on cloud. Productivity, researchers, especially things like life sciences and high energy community, they love having the environment tailored to their software stack and having that reproducibility. Containers can give that to you, but cloud makes it really easy to just spin up environments and also get isolation, make people really productive. We're going to talk about sustainability a little bit and then some technology innovations, which might surprise you, but I think they're kind of fun. And then finally, where cloud is going in terms of being more and more capable to run more and more larger fraction of the HPC workloads out there. So this is a work that we did during COVID. It was at the same time as the Gordon Bell Prize that was mentioned in an earlier talk today. In this case, it was trying to do drug screening. So during those first few weeks in April and May, researchers at Harvard realized that they had access to a drug database, but it would take them, by their estimates, close to a century to screen them all in their HPC system. So we brought them onto Google Cloud. We helped them with a auto-scaling Slurm-based cluster, and in the course of 3 weeks, they were able to do, screen, 1.5 million, 3 billion, 35 billion docking instances of 1.5 billion molecules, and narrow it down to a set of candidates that then could be fed into the pharma companies to be things to synthesize in the lab and try to develop therapeutics like the drugs we have today. And so this is an example of that urgent computing, solving a problem you just couldn't solve with the machines that were available. I think the national labs also came together and turned their resources to support similar projects. This is one that Google did on our own with Harvard Medical School. The other thing is about sustainability. Sustainability is on everyone's mind, and while I'll use Frontier as an example, it's this massive machine. It's sited at a place where there's a big dam, right? It can be very, very sustainable. But most people don't have that luxury to just source their own sustainable power. And one of the things that the cloud providers do, Google has a big focus on this, is not just source sustainable power, but actually increase the sustainable power when we build data centers. So this is an 80 megawatt solar farm in Chile that we buy all the capacity of. And down in the corner is an image off of a recent press release from 2 weeks ago where we signed a power purchase agreement for a new 700 million watt, so 700 megawatt wind farm capability off the shore of Netherlands. So we'll be using that to power data centers there. So we've been carbon neutral since 2008, 100% renewable since 2017, and on our path to be carbon free by 2030. So this is a way that you can actually reduce your carbon footprint, is just do your HPC in the cloud, because then you're getting the industry lowest PUE. It's like 1.1, where the industry standard is still around 1.6. And we've got, I think, 11 of our regions are above 85% carbon-free energy today. 11 of them are above 90%, and we have ones like Montreal that are 100%. So you can actually run on carbon-free energy. And this is true for Google worldwide, not just Google Cloud. And Microsoft, I know Andy Jones is here somewhere. Very similar commitment to sustainability and similar metrics. Microsoft and Google are leading the way here. So back to these switches I was talking about. We're going to talk about some innovation here now. This is what Google used to have to do: is these top rack switches. They're going into some kind of a fat tree here, and then it was going to a fat tree. And the downside of this was you had to deploy the spine, right? Because if you want to get the multipathing, you have to have all of these deployed. So that's a big upfront capital expense. Then when you want to do an upgrade, I want to bring in a rack of 200 gig gear. Well, it doesn't actually get the benefit of the 200 gig anywhere, because these switches, even if just one of these is 200 gig and upgraded, everything else is running at 100 gig. So what we realized was we can actually eliminate these spines altogether if we just had programmable mirrors at the top. We can do direct connect and we can program it. So some Google engineers went off and worked really hard and created a one-of-a-kind thing, which is an optical circuit switch. And these have 136 fibers that come in one side, 136 fibers come in the other side, and pairwise they can be matched up and all controlled in software with reconfiguration times measured in milliseconds. So it's not packet switching. What you're doing is you're basically wiring up the network. So now what we can do is we can bring in a single switch, and as we add racks, we direct connect them to each other. And as we add more racks, we keep direct connecting until we need more switches, then we have to switch and so on. And because these are mirrors, all these lines that are blue just light up green now as soon as there's appropriate NICs on the other end or switches. So this is what one of these beasts look like. This is a custom piece of hardware. You don't usually get to see Google's custom hardware. But here we've got all the fibers coming in. They're going into this collimator. So all 136 fibers plus some spares are fed in here. These are calibration camera modules that calibrate the mirrors. And then things come up, bounce through here, bounce back, and we can do arbitrary wire up. So this was all driven by, delaying timed capital expense, reducing power, and reducing cost. But a side effect is you can do interesting things for HPC. So one of the things that we do today is in our TPU pods, they're built on what we call, that's not on the slide, so here, I'll put it back so you don't get distracted. And our TPU pods, which I'll show you later, those are built with a 3D torus network. So sometimes you want a 3D torus, but sometimes what you'd really like is to take two slices of the 3D torus and flatten them out this way and have one dimension longer. Or maybe you want to spiral your way all the way through the torus and, just make it more 2D-ish, right? We can do that. And in fact, it's all software controlled. So when you come and you want to do a training job on a Google Cloud thing, you specify the topology and the optical switch actually reconfigures the network in response to your job to match the shape that you're doing. But there's some other things you could do. So this is an example of a dragonfly like you would find in the slingshot fabrics that Ron was just talking about. And it takes a lot of bookkeeping, a lot of care, and you have to make your network design, your topology up front, and then you hardwire the thing, right? And this system is very hard to upgrade. Another thing that's really hard to do is get isolation. So if I wanted to understand a job that's going to run on two of these groups in the Dragonfly, the fact that their traffic is moving through other blocks where there's stuff happening and other blocks' traffic is moving through them can create jitter. That can make it really hard to do, very careful performance tuning, get reproducibility. If you stick one of these optical switches in the middle of it, then all you do is you say, okay, these three, I'm going to put them in a direct connect. And I physically partition them from the rest of the network. So every link coming out is still connected to someone. I haven't lost any bandwidth, but I've gotten isolation. And that's the kind of thing you can do just with a simple call into the API. Not you, we. So, but yeah, that's an example of the kind of thing you can do with this technology. So I think it's kind of interesting. And because we went public with this, I'm expecting it's going to inspire others to create commercial products that hopefully will be available to the HPC community to start taking advantage of this in their on-prem systems. But in the meantime, we're exploiting this in ways I've talked about and additional ways inside Google. Another thing Google's done in terms of advancing networking is, progressively published over time, is a lot of things on our congestion control, our user space networking controls, all leading up to a co-design project with Intel. Ron was talking about smart NICs. This is probably the most sophisticated smart NIC that Intel's ever built, co-designed with Google to do all the things Ron was talking about. And we came public on that about a year ago, and we call that the Titanium IPU. And then the last thing that we did most recently is we open sourced the spec, and this allowed so that folks could see the reliable transport that we run inside this NIC that's compatible with our always-on encryption, our congestion control, and all the things that we're doing to address, scale in a data center, because we found that Rocky really didn't work in a cloud data center. So this gives you InfiniBand verb compatibility. It gives you NVMe over Fabric, no software changes, but down the full RDMA engine, but down on the wire, it's running a custom protocol that we developed and implemented in hardware. And then, of course, we've open sourced the spec. through the OCP, or we are open sourcing it. It's happening this quarter. I don't know if it's been opened yet. And this is the logical picture of the chip that Intel made. You can see the 200 gig SerDes, the inline crypto, which everything's encrypted at Google. You can't do unencrypted MPI. I'm sorry. Traffic shaper, which is the delay-based congestion control with microsecond monitoring on every flow, adjusting the rates. That keeps congestion. We also have a packet processing engine here that deals with spraying packets in an out-of-order arrival and limited window buffering so that we still keep in-order semantics. But we're taking advantage of the multi-pathing of our network. And then on top of it, industry standard RDME and NVMe engines, plus, of course, boring old Ethernet. And then there's a bunch of programmable cores at the top, which you can do interesting things with. Here's 16 Neoverse M1 cores, plus all the SerDes. So cloud is on the rise. You can see it's doing some HPC things. And I think over time, these things I've talked about, along with things like parallel file systems, tooling that makes it really easy to create HPC environments that are familiar and compatible, and HPC-specific machine types, it's going to make it more and more relevant for part of the HPC world. This is a picture where I'm trying to plot the capability of the system versus the capacity of the system. So my thesis here is that any leadership class machine has to be on the y equals x here, because you're building the biggest machine you can to solve the hardest problem that you can, and therefore this capability of that machine matches its capacity. And so using that approach, I've plotted most of the top 500 machines on the y equals x. And then the point of the green lines is that if you go into industry and you go into certain other fields, they don't solve a harder problem like scientists do just because they can. We always have a harder problem to solve, so it's worth it to build that bigger machine. But if you're designing an automobile and you're getting suitable fidelity on computational fluid dynamics, you're instead going to try lots of different shapes, right? So the problems ultimately push you into a place where the capacity of the machines are greater than the capability of any one job. So there's this rolling over that happens. So if you think about cloud in people's minds as effectively infinite capacity, it means if you're low enough on this curve, you can address the problem, right? In terms of the capability requirement. But as cloud improves its capabilities over time, what it does is it starts rising up with this infinite capacity, or effectively infinite capacity, and starting to basically bring things into scope. So I think we're at a point, for example, where in electronics and automotive, anyone could do their work in the cloud. Now, whether it makes sense economically in terms of a bunch of other factors, that's a different question. But we're on this path where cloud is getting more and more capable. And I think we're pretty close to the point where most of HPC can run just fine in the cloud. And that's really good news for those people. It's not necessarily good news for everyone, but it's at least good to have a choice. So there are some challenges then that come with HPC and cloud. The first one is that there is a strain on this leadership class facility model. The fact that I just showed you that you can do things in the cloud. I'm sure you're hearing from whoever provides your funding, why aren't you just using cloud? That's because the capability of cloud is rising. And I think what a lot of the people doing the funding don't understand is if you have a problem this big to solve, like that one up at the top, if you start shifting a lot of the workload to cloud, you can't keep the machine at the top busy and your economic model breaks down. And so large HPC centers have always worked on a model of give us the money to solve our hardest problems, and by the way, we'll bring the long tail of science along. And if anyone sat on an allocation board at a supercomputing center before, and I know many of you have, you know what the statistics look like of what the spread of jobs is. And it's not all leadership cloud systems. So we have to be very careful that we don't have cloud somehow eat into that and break the economic model of big machines. Second thing is what I call shadow research computing. This is an analog to shadow IT. How many people have heard that term, shadow IT? This is a term that came out of the corporate world. When cloud came along, people were frustrated with the idea that it took 2 months to discuss requirements and with their IT department, and then another month to get a purchase order, and then 4 months to wait for the equipment to arrive. Then it sat and they waited for it to be installed, tested, deployed, and they could just take a credit card out and go to a cloud provider and do what they wanted and have root, in 15 minutes, right? And so there was this whole shadow IT that rose up. The problem with it was governance, security, data leaks, people running up big bills on their credit cards. And I think we have a similar risk here in research computing, where just because cloud is more capable and getting easier to use, if the researchers start coming directly to cloud and bypassing the people who provide research computing services, including consultation, optimization, advice, then it can break this model that's been working so well for the community, which can create all kinds of problems for us. So that's something that I think we have to keep an eye on. And even funding agencies like the National Science Foundation in the U.S. are probably asking researchers use cloud. But hopefully they can do it in a way that big computing centers are actually aggregating that usage and providing value-add services. So you're getting the benefit of cloud with some controls. And I see that in some of the programs that exist in the U.S., Europe, and elsewhere, of aggregating cloud and serving it up to users. The other challenge is users expect more. Once they see this world where they can control their software environment, where they can turn resources on, and that puts strain on someone who's already dealing with the complexity of keeping a large machine going. So that's a challenge as well. And we already have a fairly thin talent pool for managing HPC systems, right? Whole new skill set now. Go learn cloud. What are you going to do with that when you're trying to run systems, an HPC system? So these are some of the challenges I see. And now pivoting over to AI. We've talked this whole week about how AI can help HPC. So I'm not going to try and cover that, but I put things into roughly 3 buckets. The first one, rather the intersection of AI and HPC, and these are very large buckets. The first one is just recognizing that AI is an HPC workload. We talked about that, right? These supercomputers are rising up to run AI. But then there's the whole AI and the HPC workflow, and I'm taking the most general sense of workflow, which is you're a scientist, you're going through the whole process of discovery. How does AI assist you? We've heard a lot of examples of that this week. And then finally, how can we bring AI directly into the workload to accelerate it, right? So that's where we can use it to actually accelerate computation, either through surrogates, through generating approximations that are later refined, so on. So I'm not going to repeat what we've heard this week, but I want to show you one thing that I think is kind of interesting that we haven't talked about, and that's this video. We'll see if it plays. So this is our latest Gemini model, Ultra model.
Is a need to find and use data extracted from the scientific literature. This is scientists need thousands of scientific papers for key information and extract them by hand. It's a very common workflow and very time-consuming. In fact, some of our scientists at Google DeepMind face this very problem. They use Gemini to help with it because Gemini has an incredible understanding of science. Taylor will explain more.
So we were looking at this study from 2022. The authors had created a data set by reviewing tens of thousands of scientific papers in genetics. They found a few hundred papers that contained the relevant information, extracted it by hand, and collected it in a table. Studies like this can take a lot of time. We needed to update this data set with what's new over the last couple of years. But that's over 200,000 new open access papers added to this domain since 2021. We couldn't do this manually, so we asked Gemini to help us out. First, we needed to filter for relevant scientific papers. We wrote a prompt, just like this one, telling Gemini exactly what to look for. With its advanced reasoning capabilities, Gemini was able to distinguish between papers that were relevant to the study and those that weren't. For the relevant papers, we wrote a similar prompt, asking Gemini to read the paper and extract the key data for us. We could even ask Gemini to add annotations. This showed us exactly where in the paper Gemini found the information. We ran this at scale. And over a lunch break, Gemini read 200,000 papers for us, filtered it down to 250, and extracted their data. So now we have a refreshed version of this data set. But because Gemini is multimodal, not only can it reason about information from text, it can also reason about figures. So let me show you something really neat. With our refreshed data set, we can now ask Gemini to update a graph from the original study. We first gave Gemini a screenshot of this figure. Then we asked it to generate the code required to plot it. And by feeding this code our new data set, we get our updated figure. You can see that this figure now includes data up until 2023.
So Taylor used Gemini to search a large corpus of literature for relevant papers and extract key information from these papers, as well as update figures. Of course, These capabilities can help more than just biologists or even scientists. They extend naturally to any domain that is reliant on large data sets, such as law or finance. So that's what Gemini can make possible, and we are excited to see what you will create with Gemini.
So I thought that was pretty cool, right? Those are real employees. There's a bunch of these videos. So I actually only found that this morning. I'd never seen it before, and I thought it was very relevant to this audience. And I went through the video in slow motion, and it's all on YouTube, and I paused it. And is my mic not on? Oh, it is. Okay, sorry. I thought you were saying it wasn't. And it generated the prompt is, you're a helpful research assistant, blah, blah, blah. And then, told it what to look for. And then the next one was here's a thing. Can you generate the code that generated this graph? And it actually, used pandas to build a data frame. And I think it was one of the plotting packages from Python. It generated the code, and then the update. It was just working in these different dimensions. And the other thing that I think is really interesting is when we have these conversational chat, we don't usually think about it, you giving it instructions. It's more like you're querying into the database. And yes, sometimes you'll ask for something, and we've heard about RAGs, right? It goes off and it retrieves the information. But it's more like for a one-shot answer. Some of the interactions I've had with the Gemini Ultra, I can actually give it a problem, and it'll say, okay, you sure you want me to do that? Because it's going to take about an hour or two, and I'm going to go do this. I'm going to read these things. I'm going to pull these annual reports. In this case, it went off and found and read 200,000 papers and hadn't been looking at them through that lens. So you can actually now do this. And the whole thing was done in a Jupyter notebook. And so I think a lot of folks think of these AIs as something you interact with through the chatbots, but you can have direct access to these models. This is true with all the cloud providers. Hook it up to a Jupyter notebook, and you can just program against it. And the way it's charged, like in our case, you pay 1/4 of a millionth of a cent 1/millionth of a quarter of a dollar. No, cent? I'll have to look again. Per character. So, you would need to pump terabytes of data through that thing before you spent as much as you would on like one DGX box. So it can be affordable for a lot of use cases. So that's a pretty cool way we can help scientists. The other one I was going to mention is in healthcare. We have this thing called MedPalm and MedLM. And so this is an example of one of the U.S. medical licensing exam style questions. So 32-year-old woman comes to the physician because of fatigue, breast tenderness, increased urinary frequency, and intermittent nausea for 2 weeks. Her last menstrual cycle or period was 7 weeks ago. She has a history of seizure disorder, treated with carbamazine. I don't know what that is. Amazine. Physical examinations show no abnormalities. A urine pregnancy test is positive. The child is at greatest risk of what are the following complications? And the people who are going to be our doctors have to answer these questions one after another. These are complicated questions. So this is there's a whole body of these questions that are used to test different LLMs. So this is that GPT Neo and Pub MedGPT. But the interesting thing is this MedPalm, that was the smaller version of the 340 billion, and then MedPalm 2, which was a fine-tuned version of our Palm 2, the one I showed you with the growing tree, is now able to do, I think, almost 87% accuracy, and this is the passing mark is 60%. So that's quite impressive, I think. And so what we've done is we've turned this into a service. We're not, unleashing it to the world because it's, interacting on medical things. It needs to be used very responsibly. But healthcare professionals, researchers can get access to this model and use it if they explain to us what it is that they want. So it's allow listed. It's public. It's available publicly, but through an access program. So the question on my mind is, could we build one like this for scientists? What were the questions that you'd like to answer that would be really helpful? Okay. So let me move on. So AI is applicable and is being exploited basically across every industry. Here's a bunch of them and the kinds of things they're doing. But I think HPC is special, and it comes back to the fact that we're building the systems that run the AI training. That's not true in any other industry. And that means that there's some interesting implications. So people probably have heard of our TPUs version 4. This is where the first pod, which was 4,096 chips with this high-speed interconnect, the Taurus I described, crossed an exaflop of BFLIT 16 performance. A little while ago, we revealed the next one, which is the Cloud TPU V5P. We have two different versions, one which is more performance-oriented, one's more affordability. This is the performance-oriented one, but you can see some of the specs. But the pod has 80 960 chips, and it does about 4.1 exaflops of bfloat 16. You can just show up and rent these. I think they're $1.98 per CPU hour or per chip hour is the price. And we've scaled models on these pods scale horizontally. And this is all those optical switches I was telling you about that dynamically rewires the optical network. The other interesting thing that's happening that AI is influencing HPC is people we talked a lot about mixed precision. TPUs don't have FP64, but people are doing research on how to work with low precision. So we have folks who are doing, Bayer doing drug discovery. This is direct simulation. This is not AI. MRI reconstructions, and this is large-scale DFTs, all being done directly, math on the GPUs. This is not for the faint of heart. This is hard programming. You're not just going to take your C code and port it over. But there's active research here, and people are getting interesting results. So I think, again, the fact that we're getting more and more of this low precision math, especially on GPUs where we have FP64 available, is a real opportunity for the community. And we heard earlier this week about some ways people are starting to exploit it. Another thing that's happened with AI is driving to bigger and bigger chips, right? These GPUs have gotten huge. They're reticle limited. And one of the things that happens when you push a chip out to the limits of the process from, say, a TSMC or an Intel or whoever your fab is that the yields go down. These are different statistical models of defects and whether they'll cause a chip to be bad. But the uniform conclusion is, if I build a big chip, the answer is bad. And so this, brought to mind what, Moore, with his Moore's Law, said something else in 1965 that was insightful, which is it might prove more economical someday to build large systems out of smaller functions, separately packaged and interconnected. And so that's what's happening in the industry. I think a lot of you know about, we heard earlier in the week about chiplets and chiplet standards. We heard from Bob and we heard from Satoshi about chiplets can only get you so far, and maybe we have to do 3D stacking. Some of these, this is an example of a 3D stacked chiplet, the desktop part, in this case from Intel, called Lakefield. But the main thing is that you can mix processes. You need standards, of course, but you can mix processes from different fabs, different generations. So you can mix optimization for performance, for cost. You, of course, get yield because you're pushing to the left on that curve. And you can get to market much faster because every chip can be validated much more quickly. It's smaller, especially for things like power delivery and thermals, which get really hard on a large chip. And of course, you have the opportunity to mix chips across generations, so it becomes a more modular ecosystem. So there's a bunch of things that are rising up around chiplet ecosystems and standards now to support this. So that's a good thing that's coming out of these monster chips. But there are some risks as well. So one big concern I have is whether the shift to GPUs is leaving researchers behind. So we've had these mature GPUs and mature software stacks for well over a decade at this point. So we're going on like 13-ish years when things got pretty robust. We now have these massive machines. We have the massive investment by the Department of Energy. It's happening in Europe with things like Supermach. I guess you're doing a massive GPU machine, right? And other places around the world. We heard from Doug Cote about the $1.8 billion investment in the Exascale Exascale computing program around getting readiness, with a large fraction of that going to software, something like 2-to-1, if I heard Doug correctly. But the reality is most HPC codes are still not ready. So we're building these huge machines that used to serve everyone, as I said earlier, and now they're really only serving the largest codes. And that's a problem. So I asked Earl Joseph, who's one of the leading analysts for HPC, he runs Hyperion Research, about just what they've observed. And they said the average technical and scientific application software is over 35 years old. And as you look at how there's, all the surveys they do, 50% of the applications still run on a single node and a quarter of them on a single core. So I see some nodding in the audience. This is what I saw. One of my friends at a supercomputing center shared their usage data with me privately, so that I could examine it to test this, and it looks like it's still true. So I also asked Earl, what are people buying? So this is 2011 to 2022, their survey data. Orange is units of CPUs, blue is units of GPUs. And you can see this little blip here when everyone was told by their CEO, you better buy an NVIDIA DGX to get on that AI train, right? That happened in 2012. There's a little blip here in 2013, and then it went back to normal. Obviously, in the last year or two, it's bumped up, but that's purely AI driving that. It's not because there's a huge body of scientific and engineering software, as far as I can tell. I'm sorry? What's that? It could be. That's my interpretation, of course. Thank you.
The cellular demand. Correct.
Yeah, but these are units, not dollars. So, yeah, absolutely. So that's kind of, are we leaving the researchers behind? It's really tough because it's non-trivial to re-architect a code for CUDA or any thing with base. Even if it's a shared memory model, the fact that the memory lives in two different places means you're moving data, and that means you have to control it, want performance, and that means you have to think globally, not locally. So very, very hard to do that. The other one I'm worried about is, are there enough flops for everyone? We talked about, ultimately what you're buying is silicon area, and silicon's not cheap. If you saw the wafer cost that I showed on that prior slide, I didn't talk to it. So NVIDIA published this recently. There aren't actual numbers, but they talk about the A100, which I think everyone knew, and they said 11x gain on GPT-3, 175 billion inference performance in 2 years. The next year, another factor, bringing us up to 18x cumulative, and then this fading into the sky, B100 later in 2024. I don't know what their number is, and if I did, I couldn't tell you, but you probably know because a lot of you get disclosures. The point is the investment that's going into low precision flops is crazy. And that, to me, means it has to be coming at the expense of something in a fixed die area. And that means our double precision floating point is not going up as fast. And so that means that we're going to, unless we figure out this mixed precision thing, we're all going to be left, on the side of the road in terms of moving science forward. So that's a big concern. And I have just a couple more and I'll wrap up. This is one I don't have any slides for. It's just a question. Is AI, AI is getting smarter, but are we? There was, I don't remember who it was. I think it may have been Ava yesterday who said, or maybe it was, I think it was Ava who said, are we at risk of losing our ability for critical thinking? And then, is that right? And I think about some of the studies that are out there, brain studies, cognitive science studies. And for the last decade, there have been people wondering, how is the internet affecting our brains? I read one that was really interesting many years ago. I can't remember if it was Nature or Science, but they talked about how they took people who had never been exposed to the internet before, did brain scans on them. Then they gave them a bunch of tasks to do on the internet, including homework every day to go home and do it. And then they had them come back periodically and scan their brains, and they actually saw their analytical parts of their minds that light up normally starting to fade, and the parts of the brain that were more primitive, like that you would see in hunters and gatherers, lighting up. And their hypothesis was that it was actually causing a reversion back to simpler times when you're doing survival things. Clicking through links, looking for information is like hunting for berries and nuts in the woods. There's been a lot of research since then, and I don't think the jury is in yet, but I think when we're in a place where you don't have to think anymore and you can just ask an AI to do the work for you, maybe it's not going to change our brains, but I know that if we don't solve hard problems, we don't develop intuition, if we don't do the research ourselves, it doesn't stick. So I'm actually a little bit concerned that if we become overly reliant on AI, that we might not get smarter. And that raises another one, which is the equity question. On the one hand, you can argue that everyone should have access to the same tools, right? And the other hand, you could say, well, this stuff's way more expensive than a web search. I'm going to charge a premium for the good version, right? And we see that, right, where you have subscriptions. Google's Gemini, you either come through the cloud or you can sign up for a personal subscription as part of a storage and other plan. I think OpenAI, Microsoft have similar situations. You could say that's an equity problem. But what about if we do make it the same for everyone? In the past, we had a distribution of people. There were exceptional people, when I mean aptitude for doing science, engineering, discovery, mathematics, whatever it is that we want to look at aptitude. And then there were more folks towards the middle and folks for the bottom. There's a distribution. If we do something where we raise the level of everyone, we naturally compress that spectrum. And that's not a problem that those folks are getting better, but I think as a community, it actually makes it harder for us to figure out who are the most capable, deserving people who should be pulled into the very few slots so that they can be groomed into the next generation of scientists and researchers. So I don't know how this is going to go over with you as a point of view, but I actually feel like there's an equity issue for the people who are the exceptional ones when everyone else is lifted up by these technologies. So something to think about. And then finally, there's this question of how it's going to impact the workforce. And I think we heard about this the other day. We said, will there still be a need for scientists? It'll be very interesting to see which things are done by AI that start to potentially cause either fewer jobs or cause people to provide money to say you don't need as many people now. Therefore, your budgets are getting smaller. And what are the carry-on effects or the knock-on effects of that going to be if AI starts changing the shape and skills of our workforce? So with that, I will wrap up. Thank you.